Exponential growth and decay can be modeled using the following ordinary differential equation, which states that the rate of change of a particular quantity is proportional to the size of the quantity. And this quantity can be the concentration of a reactant, the mass of a radioactive isotope, and so on. So when we look at exponential growth, the constant of proportionality is positive, so the instantaneous rate of change of y with respect to time is equal to some constant k by y. And applying an initial condition y equals y0, then the solution to this ordinary differential equation can be obtained as follows, using separation of variables. So we can see that the quantity y is exponentially growing at a rate k. Now the model for exponential decay is similar, which can be written as follows. And applying the initial condition in a similar way, we obtain the following particular solution. So in this case, the quantity y is decaying at an exponential rate k. And typically you'll get verbal problems to model exponential growth and decay, and we'll get some practice in the following problems. A cash deposit D grows exponentially, so we recognize that the rate of change of the deposit with respect to time is proportional to the deposit. And therefore we can separate the variables and integrate both sides. So what we get is the natural log of the deposit is equal to the rate by time, plus a constant of integration. So therefore the deposit as a function of time is equal to e to the rt by e to the c, which is just sum of the constant multiplied by e to the rt. So the initial deposit is $4,000, so we have 4,000 is equal to C1. But we substituted for T0. So let's replace C1. And to calculate how big the deposit is after 10 years, we can use the interest rate. So substitute at 2%, which is 0.02 per year, multiplied by the time in years, which is 10 years. So therefore this quantity is dimensionless, and therefore D of 10 is equal to $4,885.61. A radioactive isotope undergoes exponential decay, so the rate of change of the mass of the isotope with respect to time is proportional to the current mass of the isotope. And K is the constant of proportionality, or the rate constant. Now we have an initial mass of 15 kilos, so when you solve this differential equation, you're going to get the mass at time t is equal to the initial mass by e to the negative k multiplied by t. And given that we have 1/2 of the mass decaying after 245 years, so what we have is the mass on 2 is equal to 15 by e to the minus k by 245 years. And then solving this equation, you'll be able to get the rate constant k, which is going to have units of per year. Because when we multiply by time, this quantity is going to be dimensionless. And then how much of the isotope will remain after 700 years? Well, what you do is plug in 700 years into this equation, because we now have the rate constant and the initial mass. And you'll obtain a mass in kilograms. And post your answer in the comments.